Hello, welcome to Spider Unit Test Framework, which is basically a convenient way to do unit testing. In this presentation, I will be going through the introduction of unit test framework and how the ways in which a person can use it. So the basic goals of UTF are manual and automated unit testing, ease of use, automated UT regression testing, which is still ongoing, fault injection, the ability to create test suites, and the ability to run on SSR sim. Why use UTF? Basically, the main reasons why one would use UTF is to test anything, basically from ranging from an individual API to entire packet forwarding scenarios. UTF also provides modular isolation so that you can actually separate your tests based on the layers that you are testing. It is portable and easy to use, so that if you actually change your line card or you move from a SSR to another one, you don't have to actually change many files, and all your tests are still able to run the way they were running on the previous configuration of yours. Different debug and log levels provide easy debugging and also allow you to isolate as to where exactly your code is failing. Software based packet generation is also a part of unit test framework. We use KP for the same, and right now there is SKP. We haven't tested traffic generation or flow generation using SKP. For most of our tests, we are either using one packet or maybe two. Then the last feature that UTF has is RPL CLI integration, which allows you to send RP or RPCLI commands, so as to, if there is any configuration that you want to run through RP, you still have the option to do that. But most of our tests are using there are tests that use both RPCLI and APIs, but our advice is using APIs is the way to go. However, as already mentioned, RPL CLI integration is always there. This is basically the structure in which our UTF framework resides and how it is present on the line card. This presentation is basically aimed to help a user actually understand how to use unit test framework, so I'll be skipping this. But if someone really needs to know as to how this thing is working, the internal workings of the unit test framework, please feel free to look up the unit test framework reference doc, which is present on our page. This again is the same thing, so I'll be skipping this for a while. Yeah, this I'll explain as, because this is our basic setup is right now. So what happens is, in this case, there is a SKP server sitting on a separate Linux machine. Then there is a line card, and then there is an L2 switch. So what is happening is, the SKP server generates two packets. One is the packet that is actually being sent and which will be forwarded through the line card, and the other packet is an expected packet, which the SKP server expects to receive once the packet has been forwarded from the line card. So the flow is as follows: the packet is sent from the SKP server to the line card. When the packet is being sent, two packets are generated at that point: the packet that is being sent and the expected packet. So a packet is sent from the SKP server to the line card forwards it and sends it back to the SKP server through the L2 switch. Once the SKP server receives the packet from the line card, it compares the packet that it actually received with the expected packet that was generated. This is basically a byte by byte comparison, and once this comparison happens, and if the expected packet and the received packet are actually the same or equivalent, then in that case the test is supposed to have passed. In any other case wherein if the packet is never received, or if there is some field that is not exactly matching with the expected packet, then in that case the test fails. So now I'll be explaining each individual file. So first comes the setup file. It contains all the fields that are required to establish connection between the physical devices that you are going to use for your unit test. So so I'll just jump to the next, the actual setup.json. All files are basically JSON files, and all JSON files have a structure in which there is a key value pair. It's basically composed of classes with similar to classes in C files, and each JSON file has a key value pair. Each JSON file has an object which in turn has a key value pair. So as you can see, log value in this case is a key, and the value that critical is the value for log level. So this is how a JSON file is basically structured. For more information, you're always please feel free to refer Wikipedia. So now we go to the setup.json file. As you can see, there are many fields that have been mentioned, but the most important ones that I can show you in this short presentation are log level, There are two basic log levels, one is debug and one is critical. In the debug, there is every possible input that you have given to your unit test will be printed out. I'll show that to you once we are running tests. And the critical one only prints out whether the packet has been sent and received properly and whether the test is passed. Then we can check. Then the other one is traffic. The traffic one is yes. If you specify it as no, then the test expects that you are not generating or sending packets for the test. The traffic generator for now is KP, and we have tested the UTF framework only with KP for now. N2X support will be added in the near future. The another flag that is important is the RP flag, which has been set to false. As mentioned, as can be seen in the comment, if you need RP commands to be sent for your unit test, make it true. Otherwise, keep it as false if you are testing only with APIs. Now, the other thing that comes in the setup.json is the device is a dictionary that has devices in it. So when I say a dictionary, is basically is a hash map. Similar to what one would expect in a C program. So as you can see, devices is basically the key, and then there is a list of devices, and each device is in its own separate dictionary, and each dictionary is, as mentioned earlier, is a hash map with key value pairs. So as you can see, in devices there is the IP login and password for the SSR. Then there is the IP and login and all the fields for the line card as well. Then comes the device port map. This is the most important part of the setup.json, which you may or may not have to change. So when you are running your tests, as you can see, for the device port map, you have to mention the slot for the line card, the ports on which you are going to run your test, and everything. So if you do decide to move to a different line card or an SSR for that matter, you have to change these files, this file in particular, because you'll have to change the slot and the port. The MAC desk cookie and circuit ID, if you're using RPCLI, as mentioned in the previous case wherein the RP flag was true, if you would have put it as true, then in that case these three fields, the MAC desk cookie and circuit ID, the UTF framework would have calculated for you and you wouldn't have to mention those. But if you're using APIs, so in that case you would have set RP flag to be false, and in that case you yourself will have to mention these three fields. If you don't do this, then your test might fail, because this current setup.json has all the fields set up for line card 9 on SSR 80203993, I guess. Yeah, it has been set up for that. So if you don't rectify these files for your own unit test, none of them would work. So just to summarize, this is the main file that you need to change when you're moving from line card to line card or to a different SSR chassis. Now let's move on to the object setup file. So as can be clearly seen, the object setup file comprises of three things. The name of the object. Once again, the object is basically a kind of a class which has its own key value pairs. It has a unique name and acts as a key into the objects hash map. So objects is basically, so there is an entire table of objects in this file. This will become more clear when we move to the next slide. So for just now, just remember that there will be multiple objects, each having its own key value pair. Then the second field is the type of the object, that tells the framework whether the object will be having APIs or will be issuing RPCLI commands. Then the third field is the list of RPCLI commands if it is an RPCLI object. And the fourth field is the list of APIs that you want to execute if it is an API object. Now let's move to the object setup file. Now this would make much more sense after the previous slide. As can be seen, there is a objects list. So those square brackets, when in JSON file and Python for that matter, if there are square brackets at the start and the beginning, it's basically a list. List is basically an array for C programmers. So yeah, so there's an objects list that has 4 dictionaries, as can be seen. It has 5 dictionaries, and each dictionary itself has a object in it, and these dictionaries have key value pairs, and as can be seen, all have the same keys, but the values are different. So there are 4 dictionaries with each with 4 fields. So there's an object, As a type, there's a type, there are commands if it is an RPCLI RPCLI type object, and then there are APIs. So yeah, so that's about it. But when we move to the next file, the one thing that you should notice in this case is the object names in this file as well as in the objects.json file are the same. So if you see an up circuit object here, you will see an up circuit object in the next file as well, the next file which I am about to show you. Also remember that the commands or the APIs that you want to call will be executed in the same order as you specify them in this file. So yeah, that's one thing to remember. The next file is the objects file, and trust me, this is the last one, so you won't be bogged with many more files. So yeah, this is the objects file. So it has basically, it has the following characteristics. So it again has key value pairs, but in this file it actually contains the parameters that are required for the APIs that you specified in the previous file. Value for each parameter can be specified in the following ways. So there are 4 ways of doing that. You specify the actual value, you call a special function to actually calculate it for you, you get value for a parameter from an object within the same or parent objects.json file. Forget the parent objects.json file for now, I'll be explaining that later. So for this you will have to do the following. You'll have to specify the parameter, and then you'll have to specify get underscore parameter underscore parameter name underscore object name underscore index. Index is used when the object's parameters have multiple dictionaries. I'll get to that later. The next part, the next way of getting the parameters is getting the value from a globals dictionary. This also will be clear in the next slide. So okay, so now this is the objects. This is what an object in the objects.json file will look like. So as mentioned in the previous slide, we have an up IPv4 forward object here, and there was a up IPv4 forward object in the object setup.json file as well. So as you can see, these are the values that this object requires. So any API that will be executed that you have mentioned in object setup.json will use these parameters. So yeah, so now I'll go through the notes once. It will make much more sense once we go to the test script. But yeah, so here are the basic notes. When we call make object up IPv4 forward in the test case, all APIs or RPCLI commands listed in the objects underscore setup JSON will be executed with the parameters mentioned above. As you can see there, for the port MAC in up IPv4 forward, we have mentioned get MAC port 1. It will result in the value of port becoming 00023B06A432. This happens because as you might remember in the setup.json file, the one that I showed, which was the first JSON file that I showed, there is a port map. There's a device port map actually, and in that device port map there are 3 fields which I told you that if you do not use RPCLI, you'll have to mention them specifically, but if you use RPCLI, it will calculate those values for you. So when you specify the value of a parameter in the form of a underscore get underscore parameter underscore port or ingress or egress underscore followed by index, what you get is the actual value of that parameter for that particular port. So yeah, the another way to reference a port is using ingress or egress terms. Hence in the JSON file we can specify port and then specify get MAC egress 0, which will again give you the same value because there are 3 lists: ingress, egress and port. I'll come to that later. Now once these values are there, I mean once you create such JSON files, and when you start running the test, in that case what happens is the API is listed in the setup.json, object setup.json, which are namely forward AL next hop create connected, fib route add and IP encap adjacency create and adjacency update. They will be executed once using all the parameters that you mentioned above. So if any of these APIs require a parameter that you have mentioned in this dictionary of yours, that value will be taken from here, and those APIs will be executed with those parameters. How those APIs are actually being called or from Python, I'll come to that later. That is in the next slide or a slides after this one, or a few slides after this one for that matter. So next we come to, okay, so this was the first part. This is what you will see in a objects.json file. Then the objects.json file also has another kind of way in which you can represent a single object. So if you'll remember again, then there was an up circuit object in object setup.json. So this guy again has a list, but in this you'll see two dictionaries. So this is basically because for our test case, one of the test cases from which we are actually bringing up this example is using two ports. So we need to bring up two ports and their corresponding circuits. So up circuit actually has two dictionaries. Now, as can be seen above, up circuit has a list of two dictionaries. Please remember, list has square brackets, and dictionary has the curly ones. As can be seen above, up circuit has a list of two dictionaries. Since up circuit is an object of type RPCLI, the RPCLI commands listed for up circuit in the object setup.json file will be executed twice. One time with the parameters from the first dictionary, in which case the interface would be 1, and the second time the same RPCLI commands will be executed with parameters from the second dictionary, wherein interface would result in I2. Had the up circuit been an object of type API, the same set of APIs listed under up circuit in object setup.json would have been executed twice, but first with parameters present in the dictionary 1 and then parameters present in dictionary 2. As a general rule, if n is the number of dictionaries in a list for an object mentioned in objects.json with RPCLI calls or API calls mentioned under the same name in object setup.json, then those RPCLI or API calls are executed n times. That does get confusing in the beginning, but once you start using it, it makes much more sense. Another field that might interest a few people is the globals dictionary. So in the objects.json, there would be a globals dictionary as well. So as you might recollect, the objects.json file will have many objects under it, but there could be fields that are common to all the objects, such as in the case of IPv4 forward, there was an AFI field or the port type or whatever. So such fields you can mention in the globals dictionary. Now the advantage of doing that is you don't have to mention them again and again in each object object that you create. So you mention it once, it is available to every object that you ever create in that objects.json file. So I'll just go to the notes once. Any parameter that is common to all objects in the JSON file can be put in the globals dictionary. This allows all objects to have a local copy of the parameter present in the globals dictionary. Now the third point I'll explain a little. What happens is, since you created a globals dictionary, each object has its local dictionary in which the global variables are available. But what happens if you want to override this variable? So assuming there are 4 objects in your objects.json file, and out of this, three use AFI as 1, whereas the 4th one uses AFI as 2. Now since you have specified AFI is 1 in the global dictionary, you would feel that the 4th object was also use AFI as 1, but you wanted it to use AFI as 2. So for that, what you have to do is, in the 4th objects dictionary, all you have to do is mention the same field with the value that you want updated. So in the 4th objects dictionary, you will have to mention AFI as 2. So this would actually allow you to override a global variable for that object. But the other objects, the first 3, won't even see that change. They would always, since you have not mentioned that in their local dictionary, they would always refer to AFI as 2 in the globals one. AFI is 1 in the globals one. So they'll never. So what I'm trying to say is, if you want to override a particular value for a particular object that is present in the globals dictionary, you'll have to mention that parameter in the dictionary for that object. The next and the last part of the objects.json file that you will see is ports. So it's basically a logical port mapping to the physical ports in setup.json. So what happens is, the setup.json can have multiple ports. It doesn't. There's no limit as to how many ports you can add there. But not all tests use all ports that are present in setup.json. So if you need a particular port, what you have to do is, in the ports in this ports list, you have to make the number of you'll have to make n dictionaries, where n is the number of ports that you want to use for your particular test, and then you specify ID 0, ID 1, whatever. So when I say ID 0 or ID 1, what I mean is, the setup.json file, which we saw, which was the first JSON file that we saw, has a list of ports. So when you specify ID 0 or 1, you refer to that port in that list of ports in setup.json. So when you specify this as when you specify an ID, your test will be using that port in the setup.json, that port that you have mentioned in setup.json, with ID being 0 or 1. So if there are 8 ports in that setup.json, you can use ID as 7. So please remember that the listing or the ID start from 0. So that would be, if you want to use nth port, you would use n minus 1. Yes, and now regarding that ingress egress flag, the fields of the ports are unrestricted. You can add as many number of fields that you want, or whatever you want for that matter. The JSON files, in fact, for any dictionary that you have seen up till now, you can add any parameter of your choice, but be sure that you update your test with that parameter, otherwise the test will not work. Now regarding this ingress egress flags, there are no ingress flags, there are only egress flags. So what I have done is, there are 3 lists in which port details can reside. There is an ingress list, an egress list, and port list. When I say lists in which the ports reside, I mean the framework is doing this, so you don't have to do any of this. So getting back to there, what I was saying was, there are 3 lists in which port details can reside: ingress, egress, and a port. Port 0 has its egress parameter set to false, and port 1 has its egress parameter set to true. Hence port 0 is in the egress list and port 1 is in the ingress list. Oh, sorry. Port 0 is in the ingress list and port 1 is in the egress list. Any port that has egress field set to true is considered to be an egress port and added to the egress list. If the egress field is set to false, it is considered as an ingress port. In any case, including the case where nothing is specified, all ports are present in the port list. So you can have a port in the ingress list or the egress list or nowhere, but you'll have the port in the port list. So the port list is being the superset of both ingress and egress lists. So all ports are present in the port list, no matter what. Assuming there are 4 ports in objects.json with port 0, 2, 3 having egress set to false, then port 0, 2, 3 are added in the ingress list and port 1 is in the egress list. All ports, i.e. port 0, 1, 2, 3 are present in the port list. In order to get the MAC address of the port 2 in the port list, one can do either get MAC port 2 or get MAC ingress 1. Because when you are specifying port as the parameter, in that case you are referring to the list of ports in setup.json. But when you actually mention ingress or egress, at that point you are referring to the ingress egress list, so the indexes change. In order to get MAC address of port 1 in the port list, one can do get MAC port 1 as port 1's index in port list is 1, or get MAC egress 0 as port 1's index in egress list is 0. It was confusing for us in the beginning as well, but if you do get confused, in that case, just write it on a piece of paper. You will understand as to what I'm trying to say here. So now let's get to the main test script architecture. There are the test script. This is what you will actually be writing, and the previous parts are and the JSON files which I explained will be the ones that you'll have to modify or bring up new JSON files to actually run a single test. So the test script has basically 3 things: setup function, a run function, and a tear down function. The setup function is responsible for reading the JSON files to get the API parameters and call make object to execute the APIs or the RPCLI commands in the order they are mentioned in the JSON files. The run function is wherein you can actually generate a packet if you are actually testing with traffic. The tear down is wherein you actually destroy all the configurations that you did in setup. So that's about it. That is how the test script should look like, and it looks like that only. So I'll just go through this once. In setup, the following things are done. You read the JSON files, both object setup.json and so you read 2 JSON files basically. The third one, the setup.json, is read automatically. You don't have to do anything with that. In setup, you read 2 JSON files. The first one is object setup.json for finding out which APIs to execute, and then you read objects.json to find the parameters for the APIs that are going to be executed by calling get utf-config with the file names. The function returns a utf-config underscore entity that has all the information that is provided in 3 JSON files, namely the object setup, objects, and setup.json. This config entity has all the objects that were specified in the above mentioned JSON files with all the parameters that these objects require in the form of a giant hash map retainer. Retainer is actually internal to the infrastructure, UTF infrastructure, and there is a way to access that, which I'll be going through next. But what I'm trying to say here is this get UTF config function. What it does is the files that you used, the objects JSON and object setup.json. The objects JSON, sorry, the objects setup.json had the APIs that were required. Now these APIs require parameters which are specified in objects.json. So when these two files are read, that combination of APIs and the parameters that they require, all that thing is done here itself. So when this function returns, you have your function calls or the API calls ready with the parameters that these API calls require. In order to, now as I mentioned, there is a hash map, so which you might or might not require for your test. But in order to access any parameter that is present in the objects.json file, such as your fib id, adjacency id, or whatever, in order to access that, one has to, if you just want a particular value that you have mentioned in your JSON file, all you have to do is call get underscore object function for the UTF config entity with the object name, the parameter name, and the index. So in this with an example, this is how it looks like. So adjacency ID is present in up IPv4 forward. So you can do UTF config underscore entity dot get underscore object with up IPv4 forward being the object name, adjacency ID being the parameter that you require, and the index 0, which would actually give us adjacency ID equal to 0x3, which if you see in the previous slides is the exact value. Now things become interesting when the object has a list of dictionaries, as was the case in upcircuit. So if you want to refer to a particular parameter that is in one of those dictionaries that are present in the list for that object name, then you have to do this. You say UTF config underscore entity dot get underscore object with this object name, the parameter name that you require, in this case interface, followed by the actual index of the dictionary whose parameter that you actually want. So in this case, interface is equal to I2. Whereas if the index would have been 0, then in that case the interface would have been I1. Once the UTF config underscore entity is ready, you have to execute the APIs. So in order to do that, all you have to do is just call UTF config underscore entity dot make object with the object name. So in this example, I'm trying to make object up IPv4 forward, which will execute forward AL next hop create connected, forward AL IP fib route add, forward AL IP and cap adjacency create, and forward AL IP and cap adjacency update with the parameters mentioned for up IPv4 forward in objects.json file. Also, please remember that all constructive things are done in setup. If you try to remove something that is not there already, you might crash the line card. At least that is what we have observed. In the run function, all you do, in most of our test cases, we have actually generated packets and sent them. And in the tear down, all the destructive things that you want to do, at least for your test, don't do anything else, please. Yeah, all the things that you want to do are done here. So in this case, we are actually trying to, in tear down, we are trying to run down IPv4 forward. We are trying to make that object down IPv4 forward, which will execute the following APIs, which are basically IP route delete, next hop delete, and adjacency delete, with the parameters mentioned in objects.json for down IPv4 forward. Now, before we move on, I'll just execute a test, show you the basic test that I was referring to, and how the test actually is run and how to run it. So now I'll demo how to run a basic test case for that matter. And what we'll do, as you can see, the RP flag was set to true. And now what we are doing is we'll actually run a test case that requires RP CLI. And the example taken is test IPv4 forward.py, which is under UT IPv4. So we change the directory to testlc, and to run a test, all you have to do is use the init test.env script followed by the test that you want to run. Also, as you can see, what we are trying to do is actually Scapy is capable of sniffing packets. So what I'm trying to show here is that how to sniff packets using Scapy. So now the test starts, and this is with the log flag set to critical. So only the most important things are shown and not everything else. So what parameters are passed to the API and all, that's not shown. As you can see, SCAPI generated a packet and received one as well. And as it can be seen, UTF-SCAPI server says packet received, and as a result, the test is passed. Now I'll just change the config setup.json under config to show us everything. Actually, yeah, let's do that first. So I'll change that to debug. So now you will see all the parameters and to all the parameters that were passed to the API, along with the APIs that are being executed and whether they are a success or a failure. So these are the initial RPCLI commands that you had added for the test case. Each command is being shown, the output of that command is also being shown. So now as you can see, the APIs are being executed and all of them are a success. So SCAPI starts generating a packet, the packet is sent and it is received. Now the down IP4 or destructive part begins and the test passes. So when we are sniffing using SCAPI, you can also see as to what the MAC address and all the details that were put on the packet are also available. So you can see that as well. So SCAPI is not just a packet generation tool, it actually turns out to be pretty good sniffing tool as well. And the logs that you see will be present on both. The printout that you see actually has both shows you the packet that was generated and what was expected out of it. And yes, you can again see as the result as the test has passed. Now let me try and run a test that has only APIs, that doesn't use RPCLI. So for that case, the first thing that we need to do is set this flag to false. Do remember that if you don't do this and try to run an API test case, it is bound to fail because because during our initial setup, the RPCLI commands will be executed and it will actually create a port, and even the APIs will try to create a port and it will just fail. So please don't do that. Do change the config setup.json to config setup.json's RP flag to false if you are using APIs only. Now let's try and run a test that actually has only APIs. So the one that I'm running is test IP for forward underscore API.py. Yeah, Python files have the extension called .py. So yeah, this is being run with debug flag as critical, so it won't show you everything. But what we are trying to show you here is that even if you just change the RP flag to false, the test will run with only APIs and will not issue any RPCLI commands. Now I'll just change the flag to debug again, and so that you can see all the parameters that are being passed. Let's run the test and see what happens. And yeah, so now you can see all the APIs one after the other with the parameters that have been passed to them. As you would have just seen, the SCAPI server sniffed two packets, the one that was sent and one that was received. And yeah, so all the APIs are being executed one after the other. One more thing to notice here is that you'd see UTF log at the beginning of each line. So what this signifies is that everything that you type or everything that you see on the screen is being logged in a log file, and that log file is under tests lc logs. So any test that you run, if you see something with UTF log as at its beginning, you will find that in your in the log file for that particular test which you just ran. So the test is still, in fact, it's just the output that is being shown so slowly for some reason on my office machine, but the test has run because it has sent and received all the packets. So yeah, and yeah, so as you can see, the test has run. I'll just show you the logs. And yes, so as you can see, these are all the log files that have been generated. And let's just open one of the log files. This is without debug being set as without log being set as debug, so you see only the critical things. But when we, this is the log file, the next log file I'm going to show you has log as debug. So as you can see, it has every API that has been called with all the parameters possible. So yeah, this allows you to actually debug and focus on the areas that you want to actually find the faults in. If you just want to see if the API is passing or not, you can change it to debug. If you just want to see whether the packet is being sent or not, you can just change it to critical. So that's how it works. Now we're going to discuss how to call C APIs from Python. Basically what we'll discuss is Swig, how to use Swig to wrap C APIs, the files that are required for swigging the APIs, basically the dir.mk file, the ppald the plugin help functions.h, the plugin help functions.c, and utf-eppld handlers.py, which is actually the Python file where you'll be writing your handlers for APIs. Just to mention, this utf-eppld handlers.py file is present in plugins lc, plat asg lp common ald pd interface utf python plugins lc. So yeah, a long path again. So yeah, what exactly is Swig? It is basically a compiler that turns ANSI or C++ declarations into scripting language interfaces, completely automated, and it produces a fully working Python extension module. What languages it is confined to, it's actually language neutral. Swig can also target TCL, Perl, etc. Attempts to eliminate the tedium of writing extension modules for different languages. So how to use Swig to wrap the C APIs? So basically these are the files that you want to look at. The first one is plat asg, or I'll just skip the path. It's in it's the dir.mk file. The path is mentioned on the on this slide. So it contains the header files and the paths to the header files for the APIs you want to swig. Then is the eppald pre.i, which contains the name of the APIs that you want to swig along with some preprocessor definitions. Then comes plugin help functions.c. So basically this is, I'll explain this later as well, but this file is used to write helper functions for APIs that use pointers to structures, arrays, or other data types, and to declare and define structures required for these helpers. Add these helper function names to eppld pre.i and also provide the path to the header files that these functions use in dir.mk. So you have to do this the same way you are doing for your normal C APIs. Also update the header file, i.e. plat asglp common ald pd interface utf eppld include plugin help functions.h to have the declarations of these helper functions and helper structures. The last one of this whole swigging part is the utf-eppld handlers.py, which creates a so in this you have to create a function with the same name as that of the API and put handle in front of it. So if you have your forward AL next stop create connected, you will be actually using for handle forward AL next stop create connected, and you'll be passing params and config object as the parameters to this function in the utf-eppld handlers.py. And within that function call, the actual API is called. So there is an eppald module, epp_ald module, which has all the swigged C APIs. So in order to actually execute the C API, what you have to do is you'll have to call epp_ald dot, or yeah, you understand, forward AL next stop create connected, and then you'll have to pass all the parameters that are required for this API. So when I say the params here, I mean the parameters here. I actually am referring to the actual parameters that you have mentioned in, that the API requires. And how do you pass them? You actually pass them using params.get, and then you specify the name of the object. Now when I say name of the object, as you can see there is a fib id and all. Now where is this fib id mentioned? This fib id is actually present in the JSON file, the objects.json file. So this is where the API actually gets its parameters. So when it is executing and when you say params.get fib id or whatever, at that point it actually gets those parameters from the JSON file and then it calls the API. So this I'll be explaining in a little more detail in the next slides. So now let's have a look at the dir.mk file. So for now let's assume that we are trying to swig forward AL next stop create connected. So here, so as mentioned, we have to specify the H files that we need, and then we have to in the header under headers HDRS we have to specify where this file lies. So you'll have to give the exact path. Then I mentioned the pre.i file. We have to actually put in the APIs that we are calling. So the first one, the forward AL next hop create connected, is the actual API that you need to run, while the other one called make forward AL result entity adjacency lag, that is not an API, that is not there in your source code, but that is basically a helper function that you have defined in plugin help functions.c and h to actually run, to actually help you call forward AL next hop create connected. So basically it is make forward AL result entity adjacency lag is a helper function, and that is not there in your source code. So even though it is not there in the source code, you'll have to mention it in EPP underscore ALD underscore P.I, because if you want it to be swigged, you have to mention it here. So now comes in the plugin help functions.h. So basically it's a standard file. There will be some headers. There are some headers, and as you can see, what you have to do is you'll have to kind of declare that okay, there is this guy, this your helper function. So you'll have to provide it as seen in this file. You'll have to just declare it, and definition will be definitely in the C file. So in plugin help functions.h, if you write a new header, you have to declare it. Now comes defining of the function. So what we are doing is, actually, okay, this will be more clear if I go to the next slide first. So in the next hop create connected actually requires three values. It's a PFE ID, the next hop ID, and then there is this result entity. So when I say result entity, it's actually a data structure, as you can see below. So it is basically a data structure that you need to pass to forward AL next hop create connected to call this API. Now if you want to call, Python doesn't understand C pointers, neither does it understand C structures. So that is the whole reason why we are swinging the APIs and everything else. So so in order to do this, in order to actually first pass a pointer to this API, what we need to do is create a helper function, and that is what we have done in plugin help functions.c. So what we do is we just say okay, it's a basic function which actually allocates that much memory, which is equivalent to the size of forward AL result entity. Then so we create a pointer, we malloc the size of it, then we memset and memcopy whatever we need to, and then we return that pointer. So the basic point to be noticed here is that we are returning the pointer to forward AL result entity t, and that is what we are returning. So our function plug in this guy called make forward AL result entity adjacency lag is actually returning a pointer to forward AL result entity t. So please remember that, because it will be this thing will come in the next slide as well. So yeah, so in your UTF EPP ALD handlers, this is the API that we are trying to call with the structure. Now this is where you actually write the handle for that. So what you do is, as mentioned, you create a new function called handle forward AL next hop create connected with params and config object. You call debug params with params, which actually this is what you'll always have to do. You'll have to do this debug underscore params with params. It will just print out everything if you need it, and this prints those parameters only when the debug is set to the debug flag is set to critical. The log flag is set to critical and not debug. Sorry. It prints out all the parameters only when the log flag is set to debug and not critical. Now, that is just the debugging part. Now comes the main part of the handler. So what I'm doing is in the UTF overlay allows you to actually convert those structures, the one in the previous slide, this one to something that Python understands. So what we did is we used the C underscore struct function which the UTF framework is providing to actually convert that function to convert that structure entry into to convert the structure forward AL result entity t into something that Python can digest. So its entity adjacency has that structure in it, and then you can fill those values as you would you can fill the values of the individual field as you would fill in your normal C structure. But the main thing to observe here is you are actually doing params.get adjacency ID, adjacency cookie, and circuit underscore ID and lag table ID. When you do this, it is actually getting the values from the objects.json file. So by the end of this, you have your structure populated with the values that you need. Then we call EPP underscore ALD dot make forward AL result entity adjacency lag, a long name for a function again, which basically is the helper function that you wrote. So now what it is doing is, and if you remember, it is actually returning a pointer to the newly created data structure, the result entity structure. So now ENT has that pointer. It is the same pointer that forward AL next hop create connected needs. So now we have the pointer to the function that we actually want to execute. Then for PFE in params.get PFEs, it is basically this for is similar to a for loop, and it is actually this API forward AL next hop create connected will be called for both PFEs. And if you see the objects.json file, those PFEs are mentioned in the object for this particular API. So what we do is we actually call EPP underscore ALD dot forward AL next hop create connected and give it all the parameters that it requires. And here if we watch carefully, the ENT adjacency is the pointer that forward AL next hop create connected required. So now it has all the parameters that it required. This actually results in executing the API with the parameters that you supplied, and whatever is the result of the API execution, that could be 0, 1 or whatever success or failure value, integer value that you decide, that value is then thrown back and it is collected in the error variable. Then on basis of what your error variable is, the value that the API returned, you show that as a pass or a failure. And this is how you actually swig your APIs and how they are actually executed. And yeah, some people were of the had initial doubts that whether we are actually executing the APIs or not. But yeah, we are executing the APIs. We have not altered any C code in this procedure. The only C code that we have added or modified for that matter is in plugin help functions.c. So yeah, so that's that. This is basically the steps what you need to do in order to get the line card and the UTF image and how to run your first test case. It is pretty self-explanatory, so I guess I don't need to explain that. Yeah, so now we come to the next part, but before before that I'll just okay, let's do this first. So in the directory structure, so now I'll try to explain the directory structure and the advanced features. So those advanced features are namely two for now. They are layered architecture and the multiple values for one parameter. I'll come to that in the next few slides. So the directory structure is basically this, and this is what you'll be modifying or editing or whatever. You can create your new files if you want. So, but yeah, in tests LC there are 4 directories. There is unit test or UT, then there is utils, then there is logs, and then there is config. Logs has all the logs of the test cases that you ever run. Then there is utils, then there is unit test. Unit test has 4 directories again, which are IPv4, IPv6, MPLS and lag. Same thing happens in config. So config has all those objects.json files. So all our objects.json files will be in IPv4 folder under config. All objects.json file for IPv6 test cases will be in config folder under IPv6. Similarly for MPLS and lag. Now the infra part actually contains the objects underscore setup.json for each individual test. And so in this case what happens is, why do we have a separate folder for the objects underscore setup.json? Because your parameters for the APIs might change, but for a particular test case there is a high probability that your APIs or the order in which you call the APIs won't. So objects underscore setup is basically responsible for calling the APIs in a particular order, so you keep that in infra. While all other objects.json files actually have the parameters for those APIs and they can change, so you keep them in their test specific directories. Under config, the setup.json is also present. So this is where you actually change your, this is the file that you need to change if you move to a different line card or a different chassis. Now I come to the layered architecture part. So it's basically, this is actually an extension and it is not compulsory. You can still put everything in one objects.json file and the other one in objects underscore setup.json file. But what this does is, what layered architecture allows you to do is, so if you have an existing lag test case, or with lag you're bringing up a lag group, and if you want to use that lag group in an IPv4 test case as an egress port or something like that, what this allows you to do is develop an IPv4 test case that uses the lag group. So you don't have to write an IPv4 test case you don't have to write a complete IPv4 test case with with lag in it. If there is a lag test case already that brings up a lag group, you can use that in your IPv4 test case and build things on top of it. So what we have tested, or what the test cases that we have till now, has the following combinations. It can be a lag IPv4 MPLS, or a normal circuit IPv4 MPLS, or it can be a lag IPv6 MPLS, or a normal circuit then IPv6 then MPLS. So this is what we have in the layered architecture thing, and how we do that, I'll just show that to you. So what I'm trying to show here is the lag architecture and how it is useful. So yeah, so as you can see, the test that I'm talking about is test IPv4 forward underscore lag underscore API.py. And as you can see, this has your set of your normal functions called setup, tear down, run test. And yeah, so you don't have to alter any of the lines from 139 to 151, and preferably you won't even have to alter any of these initial imports. Basically these are just similar to include files. So yeah, that's about it. So what changes you'll have to do is from line 27. I mean, for any test case, that is where you'll have to change things. So as you can see that this is the get UTF config which I've mentioned. So this is what I'm talking about. We imported that file as configurator. So Python allows you to import any file with a different name. So we call that as configurator, and under configurator we have a function called get UTF config. Using get UTF config, we read the two files that we wanted. Then we also read, so okay, in this case we had a lag test case already. So what we read was these two JSON files are the ones that are required for the lag test case, the basic lag test case. Now what comes next is we try to read the JSON files for the IPv4 test case, because please remember we are trying to construct an IPv4 test case on top of lag. So what we do is we first read these two files, the lag ones. We get a UTF config entity. You name it whatever you want to. We get a UTF config entity. Now that UTF config entity is used as a parent for the IPv4 part. So using that UTF config entity which we gained in line number 27, we again call get UTF config, but this time we pass this parent object called UTF conf object while reading these IPv4 JSON files. So what happens is your IPv4 JSON files, if there is some field called underscore get underscore something, and that's or underscore get underscore some parameter, and that parameter is not present in your IPv4 underscore setup IPv4.json, what happens is it searches for that parameter in object setup lag API, objects lag API.json. I'll just go do that once again. When you are actually making that object, or you are making config object underscore IPv4, and you are reading those two JSON files, those JSON files are read, and when the object is being created, it has a parent called self.utfconf object, which you created in the previous line. So when those JSON files are being read, specifically IPv4.json, which is the objects.json file for IPv4, at that point, if there is some parameter that is requested in the form of underscore get underscore parameter, and that parameter is not present in your objects.json file, in this case IPv4.json, what will happen is it will go to the parent. The parent here is utfconf object, which is nothing but the lag object, and that lag object is created in line 27. What it does is, if it doesn't find that object in parameter in IPv4.json, it goes in the object that was created, that is its parent object, searches its JSON files, that is object underscore lag API.json, to find that parameter and then return it. Once that is done, you just simply make all the objects that you want present in those JSON files. So this is the standard way of doing it. So, and this will remain same for each and every test case. In tear down, you just do the destructive part. You call down IPv4 forward, down lag group, down circuit single, down port. The tests have been explained more elaborately in the reference document. In the run test, as you can see, this is how you generate a generate and send a packet. In the test case, as you would see, there's a packet being generated. This has been explained in the presentation as well as the reference doc, so I'll just go through it once. You just generate a pack. First you configure a send port, the port on which you actually expect to send the packet. You get a receive port, then you actually send a packet. The send packet is actually created using this format, which is ether, then IP, then TCP, then padding. So this is the best part about Python, is where you can just, and best part about Scapy as well, is you can just stack one layer on top of the other and you'll have a packet at the end. So then once you have the send packet generated, the send packet is generated in line 69. Once you have that generated, you can override each of the fields, such as source, then destination and source IPs. Then you would actually generate an expect packet, which you expect to receive on the other side. And this is what Scapy compares with once the packet is received. So then you'll have to specify as to what that expect packet should look like. So once you're done that, you call myPacketGen.utf send receive to actually send and receive a packet. And it returns a success or a failure status. So if the byte by byte comparison is actually a success, it would return 1, otherwise it would return 0. Depending on that, you actually find out as to whether the test was a passing, or whether the test was a pass or a failure. The same this being a lag test case, we are actually generating 2 packets, but in the other test cases you might see 1. So it's totally up to you as to how many packets you want to generate. Traffic generation, as mentioned earlier, has not been tested, but I don't see any reason why it won't work. So the last advanced feature is one parameter when values. That is, this slide is also pretty self-explanatory, but what we are trying to do is, suppose one wants to run test IPv4 forward with 25 IDs, and this is just an example. So in the default way, you'll have to actually create those many objects.json files and have those many test cases to actually run that. But that is a very tedious and inefficient way of doing things. So the UTF infrastructure provides a convenient way to overcome this problem. Remember that UTF config underscore entity make object actually results in the execution of APIs. This results in execution of APIs with a single test of parameters, with a single set of parameters specified in objects.json. In order to run the same test with multiple fib IDs, one has to do the following: identify the object that has that particular parameter. In example, in our case, fib IDs under up IPv4 forward. Once that is done, select 3 values: the starting value, the number of fib IDs you want to generate, and the difference between each fib ID. Then make a list in the following manner, with the fib list is equal to, it's actually a list with a dictionary within it, and the dictionary is the parameters value is again a list. So this is Python jargon. You'll have to get acclimated to it, but yeah, it'll come slowly. So yeah, that's fib list. That fib list actually has 3 values in it. So in the fib list, there is the value parameter that you want to change with each test, the initial value, that is 0x3. Now how many fib IDs you want? So let's say we want 10 fib IDs, and and what is the difference between each fib ID value? So let's assume that you want them to just increment by 1. Now since fib ID is an up IPv4 forward, when calling make object up IPv4 forward, one must call make object with up IPv4 forward, and the change here is you'll have to specify the fib list as well. This will execute all APIs listed under up IPv4 forward 10 times with 10 different fib IDs. Another way of specifying the same fib list is as follows, wherein you specify fib ID followed by x0, x3, 0x4, 0x5, 0x6, 0x7, 0x8, 0x9, A, B, and C. So it's the same thing, just a different way you can specify things. This list can have multiple parameters as well. It can have the fib. You can just bring together things such as fib ID, adjacency IDs, and all, and it'll generate those many combinations and then call that API that many times. So in this case, since there are 2 fib IDs and 2 adjacency IDs, the up IPv4 forward APIs will be executed 4 times because it will have a combination of 2 fib IDs and 2 adjacency IDs. So this is this feature can prove useful in many other cases. We haven't had the time to actually write a test case for this, but it works with any existing test case. So please feel free to try it out on any existing test case. The last part is the available tests that we have. The tests that we have are IPv4, IPv6, MPLS and lag. The last thing that I'll be talking about is the team. So tests available are the test which UTF currently supports are IPv4. That test basically forwards a packet by establishing a path. Same thing happens with IPv6. MPLS test case actually sets up a static LSP forwarding path by sending a packet, and then there are two more test cases that have been well documented in the UTF reference doc. The last one is lag. The lag cases, the tests, the lag config. Okay, it basically tests the lag configuration by sending two packets, one after the other, through two different links. And yeah, so these are the tests. And now the team. So we'll start with our senior manager, Mr. Arun Sharma, with the person who actually got allowed us to work on this internship, Mr. Sevara Murthy. Then our mentors, Mr. Mike Alport and Mr. Abhishek Gupta. This is me, Abhishek Jain. I'm the intern who was filming the scrappy video. And then there's Paresh, who is also an intern, and we both were responsible for working on the unit test framework. I was personally responsible for modifying the framework, while Paresh was responsible for writing the test cases. So yeah, so that's about UTF. Hope you like it, hope you use it, hope you modify it, and hope you do something with it. So that's all this video is about. Thank you so much, and thank you for your patience, because this has been a pretty long video.